This video is going to be an introduction to the normal distribution, looking at how we can use it to calculate probabilities and do some reverse problems as well. There'll be future videos looking at some more complex examples. So the normal distribution is something that's used to measure, represents continuous random variables. That's data where it can take any value rather than just taking discrete values such as integers, such as when you're rolling a dice, you can only have 6 values. Here, this is more set to if we're measuring heights or weights or something like that, where the data can take any point at all along a scale. So if we think about the heights of adult UK men, if you were to plot the number at each height on a histogram, you'd probably get something that fitted into that sort of pattern. Obviously, a histogram would have bars, but if you took narrower and narrower and narrower bars, if your population was big enough, you'd expect to get something like this. This is called a bell curve. It's what we use to represent this normal distribution. Now, what would we have to know about this curve in order to do anything with it? One thing we'd want to know is the mean, i.e. what's the average height in our case here. So I'm going to tell you in this case, I might be going a bit short. I'm going to tell you the average height is 160 centimeters. I think that's probably a little bit low, but we'll go with it. It's going to make our numbers a little bit easier. And so that tells kind of a location of our peak, but it doesn't tell us everything because we don't know how spread out the data is. The more spread it is, the flatter our distribution is going to be. The less spread out the data is, we're going to have more and more people close to 160 centimeters and not many people who are really tall or really small. So we want to know something there. Our main measure of spread when we're working with continuous data is standard deviation. So that's what we're going to work with. So in this case, I'm going to tell you that if X is the height of a random UK adult male, then it's normally distributed, and so the N tells us it's normally distributed, 160 is telling us the mean, and then I'm going to tell you the standard deviation is 5. Something a bit weird happens in this notation here. We happen to write 5 squared here, because this thing here, we're writing the variance. You might see that as 25, but often they'll be nice and give you it as 5 squared, so your standard deviation is obvious there. So how can we use this to calculate any probabilities? The great thing about a normal distribution is if we know the mean and we know the standard deviation, that's all we need to do to work out any probabilities. So what might we be asked to work out? Well, we might be asked to find what's the probability that X is equal to 168. Well, let's think about whether this makes sense. If I'm saying what's the probability that someone's height is 168 centimeters, it sounds like a sensible question. But we're saying really what's the probability is exactly 168 centimeters. And so that means it's 168.0000 centimeters, and we could add as many zeros as we want. The more and more accurate we go, the less and less people we'd have with that height. And if I keep on and keep on going, the probability someone has that exact height is going to get smaller and smaller. So when we've got a continuous distribution like this, we're never going to ask this sort of question. We're not going to ask the probability someone has an exact height. It doesn't make sense. We'll only be able to ask what's the probability they've got height in a range that we're looking over. So a different question that we can certainly ask is what's the probability that the height is less than 168 centimeters? So here we're saying we've got some point, 168, what's the probability we're to the left of that? Didn't mean to draw a wonky line there. So the beauty of the normal distribution is that all that matters is how many standard deviations above the mean we are. So if we look here, we're going 8 above the mean. Well, our standard deviation was 5, so we're 8 divided by 5, or 1.6 standard deviations above the mean. I'm always going to write a number of standard deviations above the mean as Z. That's a standard convention. If you do that, any examiner will know what you're doing. And we're actually saying what's the probability that the number of standard deviations, Z, above the mean is less than 8 over 5 or less than 1.6. And to work this out using your calculator, and you may be thinking, my calculator does this anyway, but this will give you a better understanding of what's going on. So go to your distribution part of your calculator. On the graphical calculators, you want to go to statistics and then go to distribution. go to normal, and you want to choose your NCD option, the normal cumulative distribution option. Now, it'll ask you for a lower and an upper. The lower, I'm going to put as a very low number, so something like -999 or something way off to the left-hand side. Upper, we want to go up to 1.6. And then it will ask you for sigma and mu. Now, sigma represents standard deviation and mu represents mean. But if we're looking in terms of the number of standard deviations above the mean, as we've done here, with p of z is less than 1.6, I just want you to leave sigma as 1 and mu as 0. So if you do that, you should find you get an answer of 0.9452. So that's coming out just by putting 1.6 as your upper and leaving sigma as 1 and mu as 0. You can save time. I'll be upfront. You can save a lot of time here, well, a little bit of time, by putting in your upper as 168 and putting in your real mu as 160 and your real sigma as 5. You should find it gives you the same answer as having that sigma as 1 and mu as 0 by putting your upper as 1.6. The reason I want you to think about it this way is when we don't know our mean and standard deviation, this way is going to have given you a much better understanding. So there, we're getting one. I just want to go through a couple more examples of probabilities. So what if we're asked for the probability that x is less than 158? Well, why have I chosen this? There's something different here, because we're below the mean here. So I'm still asking what's the probability to the left of this, but if I'm looking below the mean here, then when I'm saying how many standard deviations above the mean I am, well, I'm not. I'm going below the mean by 2, so I'm 2/5 of a standard deviation, or 0.4 standard deviations below the mean. So that I'm going to represent as negative 0.4, and I'm saying what's the probability of my z? The number of standard deviations above the mean is less than negative 0.4, and now you're going to go through the same sort of thing you did before. Leave your lower as something really low, put your upper as negative 0.4, leave your sigma as 1, your mu as 0, and you should find you get 0.3446. Final probability calculation I want to look at here is what if you're asked for something between the two. So what if you're maybe asked between 158 and 168? You've got a choice here. You can either convert it to z and say this is 0.4 less than z less than 1.6 and put in your lower as negative 0.4 and your upper as 1.6. If you'd already got these answers above, you could have just done the probability is less than 1.6, subtract the probability is less than negative 0.4. But it's probably quicker there to put in your lower as negative 0.4, your upper as 1.6, and it'll give you your answer straight away. So if we want to calculate probabilities, then we're absolutely fine. We can have slightly different questions here, though. We can be told the probabilities and need to find the value that we need to be in there. So I want to stick with the same distribution. We're still going to think we've got a normal distribution with mean 160 and variance 5 squared, or standard deviation 5. But this time, I want to say, well, how tall do we have to go? What point do we have to go to where only 5% of people are taller than that point? Note, that's the same as saying 95% of people are shorter than that, or 0.95 of people are shorter than that. So if we're trying to find that point, this is where you should see on your calculator where you had the NCD option, normal cumulative distribution. You should have an inverse normal option, or just it might say inv n. So in terms of doing this, we want to think, well, how many standard deviations above the mean do we need to go? To get this, if you go to your inv n option, you'll either, depending on what calculator you're using, you'll either just be asked for an area, and that's always saying the area to the left, or you'll have a choice to say whether you're looking at the area to the left or the area to the right. I'm going to think about the left area here because we've got it labelled here. The area to the left at this point we want to be 0.95. So on your calculator, put the area as 0.95. And again, I'm going to say for now, leave your mu as 0, leave your sigma as 1. And if you press execute or equals, then you should get an answer of 1.645. What that's telling you is we're going 1.645. Sorry, my pen's just getting a little bit dodgy there. That's 1.645 standard deviations above the mean. So we know our standard deviation. We know our standard deviation was 5. So this point here is 1.645 loss of our standard deviation, or 5 above the mean. So this unknown point here is just going to be 160 plus 1.645 times 5, and you should get an answer of 168.2. That's telling us that 95% of people will be less than 168.2 centimeters, and 5% of people will be taller than that. Again, you can shortcut it on your calculator by by putting in your mu as 160 and your standard deviation is 5. But I'd recommend doing like that for now, because when we don't know the mean and standard deviation, which is going to come up in the next video, that's going to be a really useful way of approaching it, and you'll be stuck if you only understand it the way. All right. Thank you very much.